The ratio test is one of my favorite sequences and series tests, mainly because it's pretty easy to use. It works for a lot of different types of series, especially series that have n factorial in them, and we'll use it later on when we talk about Taylor polynomials. We're not there yet. We'll get there. Here's what the ratio test says. We take the limit as n approaches infinity of the absolute value of, basically, we're looking to see if the series sort of looks like a geometric series. And so what we're going to do is we're going to take the ratio of the n plus 1th term divided by the nth term. And we're going to get one of a few things. If we get that this ratio is less than 1, then sort of like a geometric series, this will converge. If we get something that's bigger than 1 or infinite, then just like a geometric series, we get something that diverges. However, unlike a geometric series, if we do get something that is equal to 1, then the test is inconclusive and we need to try another test. But at least for the less than 1 and greater than 1 or infinite case, the ratio test works very well, and let's see a few examples of that. Oh my gosh, this is a nasty series. Got lots of stuff going on. Notice that we could use the quote-unquote looks like test or do growth rates to see which function here grows the fastest. Clearly 3 to the n is going to be the fastest growing function here, and because there's nothing as fast as 3 to the n on top, that will drag the series down to 0 fast enough that this should converge. So that's our guess using the looks like test, but let's use the ratio test to see what this actually does. So, ratio test, I take the limit as n approaches infinity of the absolute value of, here we go. Now on the top, remember I'm plugging in n plus 1, so it's going to be n plus 1 squared times 2 to the n plus 1 plus 1, right, because it's n replaced with n plus 1, divided by 3 to the n plus 1. Then I'm dividing by a sub n, which is just the normal thing, n squared 2 to the n plus 1 divided by 3 to the n. As you'll notice very quickly, we usually will get a compound fraction because of most of these are fractions, and so when we have a fraction over a fraction, it gets nasty and compounded. But the way we're going to deal with this is usually you can take that a sub n and flip it and do a multiply by the reciprocal. So we're going to multiply by 3 to the n divided by n squared times 2 to the n plus 1. And that will get rid of that nasty fraction. And I encourage you to just jump straight to this point by flipping that fraction in your head and then writing it. Notice that the absolute value contains everything now. Okay, let's look at like terms. Here's what I mean by that. We have polynomial terms because we have n plus 1 squared and n squared. Using Bobo-Botten or L'Hopital's rule, we can see that we have n squared, 1n squared divided by 1n squared, and so those two will go away and become a limit of 1. Pretty straightforward. Let's look at the next piece, which is 2 to the n plus 1 divided by 2 to the n plus 1. Now, something that's nice to do with these types of exponents is to rewrite them. The first one is 2 to the n plus 2, and then I have divided by 2 to the n plus 1. Rewrite. 2 to the n times 2 squared divided by 2 to the n times 2 to the first. In a way, I'm sort of reverse simplifying the properties of exponents. Remember that if I have multiplication, exponents add, same thing on the bottom. And so I'm splitting that back up so that the 2 to the n's will cancel, and then I'm left with actual numbers. And so here the actual numbers are going to be 4 over 2, which simplifies to 2. So that's my piece there. And then the last bit is the 3 to the n. Using the same trick, I'm going to have one extra 3 on the bottom because of the plus 1, and so I'll have a 3 on the bottom. This gives me a ratio of 2/3, and then using the ratio test, because it's like geometric series, this falls into the less than 1 category, or converges, which matches our guess. So pretty nice. Let's look at another example. Oh, whoa, this is weird. This is a function that we haven't seen very often, We saw it earlier when we took derivatives in the form of x to the x, but other than that, we really haven't seen this. And in fact, I'm going to tell you this now. No, actually I won't tell you. Let's see how fast this function is, and whether or not it can beat out n factorial as the fastest function we know. So clearly we have no idea as to how to do this, so let's use the ratio test. Because oftentimes if you have a factorial is a key or a clue that you probably want to use the ratio test. So let's try it. Limit n approaches infinity. Absolute value. N plus 1 to the n plus 1 divided by n plus 1 factorial. That's the a sub n plus 1. Then I'm going to multiply by the reciprocal of a sub n, which is going to be n factorial divided by n to the n. Close the parentheses. Alright, let's simplify the like terms and expand things out a little bit. This is going to give me limit n approaches infinity, absolute value. Now here, I'm going to use that same exponent trick to rewrite another n plus 1. So I'm going to have n, or I'll do it in red so it's different. I'll have n plus 1 to the n times n plus 1 to the first. And I'm going to group that with this n to the n because they're both sort of polynomial type functions. And then on the other side, I'm going to have n factorial divided by, you might remember that n plus 1 factorial, we're going to rewrite this as n plus 1, n minus 1, dot, dot, dot. But really, this n times n minus 1, dot, dot, dot is n factorial. And so I can rewrite n plus 1 factorial as n plus 1 times n factorial. You can see that this is very useful because these will cancel right away. Now, let's take a look back over here. Just kidding. We're actually going to look over here. Oh, look at that. I have n plus 1 in the bottom from my n factorials canceling, and I have n plus 1 on top from that exponent. And so those two are going to go away. And so what I'll be left with is this. Limit n approaches infinity of n plus 1 to the n divided by n to the n. Kind of a weird limit. And we can't really, you don't want to Bobo-Botten this because these two aren't actually numbers. These are variables that will eventually go to infinity. So you don't want to think about Bobo-Botten. Doing L'Hopital's here would be confusing and hard because n is a variable, so you're taking derivatives would be kind of weird. But we can rewrite this algebraically to become a little bit nicer and hopefully a little familiar. We have n as an exponent, and so what I can do is I can basically write parentheses and write a fraction with n plus 1 over n. N plus 1 over n, all to the n like that. And then this is going to be equal to the limit as n approaches infinity of absolute value, simplifying on the inside, 1 plus 1 over n to the n. And basically that simplification happened here. N over n is 1, 1 over n is 1 over n, so I get that. This is a limit that we have seen before. If you don't recognize what it is, go back and rewatch the L'Hopital's rule of video. But this ends up being e to the first. Okay, it is e. And then using the ratio test, we can use the results of this to say, hey, e is bigger than 1, therefore this original series diverges. Interesting. And because it diverges, that tells us that n to the n actually grows faster than n factorial. And then we have all the other ones, so e to the n, etc. But this is now like super fast. Okay. We don't talk about it because it doesn't show up very often, but now you know that this is actually the super fastest growing function of them all.